All right, let's get started. Good morning, everyone. So we're going to talk about today about least squares. If you recall the last session when we talked about the linear regression, we discussed that there are two methods in order to solve linear regression problems in order to find the optimal solution. And one of them was the analytical model that we use in order to minimize the E of in, so in sample error. And the other one was the geometric solution. So we're going to talk about them mostly today, and also we're going to talk about a variant of least squares, which we call regularized least square. At the end, we're going to have a couple of slides about nonlinear transformation. Also, there was an issue with one of the tutorial sections this week. One of the TAs apparently couldn't make it to the class, so we already alerted the grad office and also those who are responsible for that, and apparently they're going to make up for the course. So because there were some reports that students migrated to the other tutorial section, and that was getting full, so the students who registered couldn't make it. So yeah, make sure you just go to your assigned sections, either in the course or in the tutorial sections. All right, let's define the least square. So this is the continuation of what we left last session. So we're gonna have a data matrix of X, which has coordinates or the vectors inside as x1 of 1 up to xn of t, and then all of them are in the R space, and they are in R space of n multiplied d plus 1, and d was the size of the dimension of your feature vector plus 1, which was the artificial coordinate we added. Our target vector was y, so including y1 up to yn, and that was in the R of n. The weight vector w starts from w0 up to wd, and they are in the same space, dimensional space as your x's, so that's why they are d plus 1 space. And the model, let's see, so this is model. And the model would be, for linear regression, would be y hat equal to x multiplied w's. So if you expand this in a vector format, you're going to have x1 of t. Well, actually, this is t. Let's see. It's t. So we're going to have x1 of t w up to xn of t w. So in a perfect world, when we don't have any error for our prediction, so that's why we're going to have, in an ideal case, our y hat is equal to 1. That means that we don't have any errors. But in other situations, we have errors, and we have to express it by in-sample error, or we call it E of in, that I'll describe in the next slide. Yeah?
Could you just explain why we have the superscripts on the data matrix X? Like 1, 2...
Because it's within all the data you have, that capital D for all the, for instance, in the case of credit card, you had the past historicals for all the users. So yeah, it could be 1 to n. All right, so if we want to express our error as E of in of w, least squares provide the suggestion that we deduct the amount of error that we had between our y and y hat, which was the true value of y, and the estimated y here. And we raise it to 2, and that's why it's well known as a least square method. So if you expand this, it's going to be a summation of i's from 1 to n, y of I minus y hat I to the raise of 2. So if we present it in a vector format, so the notation would be this. And the squared error loss function can be defined finally, as you knew from the last session. So it's a summation of I from 1 to n, y of I minus the capital X transpose I multiply W to the raise of 2. So in order to solve the linear regression solution, we have to minimize that E of n of W to find a solution for that, right? And we call that optimal solution that we found W star. So let's see with our two different methods how we're going to tackle that. All right, you might wonder why we use square error with respect to the absolute error, because I had received similar questions before as well. So in general, both methods could lead you to estimate your error rate of your prediction or your estimation. However, if you use square error, it's going to give you nicer properties, nicer statistical properties that you can use in different situations when you have several type of problems. So like I brought up like two examples just to have a better idea why we use least squares more often than the absolute error, just to have a better clue of the background about that. But if you want to have more knowledge, you can just refer to that statistical textbook of Boyd, or there are tons of materials online. Just Google for the difference between least squares and absolute error and why we use that, or in neural network L1 versus L2. All right. So one of the advantages of having least square is, suppose if x was a random variable, so if you use least square, the estimator that minimizes that using least square at the end for a random variable becomes the mean of that. Whereas if you were to use the absolute error, just like y minus y hat without the without raising to 2, you would have median for your absolute error. And in general, in statistics, mean gives you a lot of more freedom if you want to do other calculations, such as if you have the mean here as your estimator, you would be able to just expand this e of x plus y up to e of x plus e of y. But this won't be the case if you were to use the median in a case which was the outcome of using the estimator with the absolute error. So that's one of the properties you might consider. That's why people are using least square more. Another advantage would be if you have still those independent variables. If you use a square error, that becomes, and if you estimate your variance as variance x plus y, you'll still be able to expand that to variance of x plus variance of y. Whereas if you were to use absolute error, you wouldn't be able to do that. There are so many other statistical reasons that it takes like half an hour to describe. But just for now, you can see in general when people are using least square instead of absolute error, that's because they are giving them some nicer statistical properties. Also in signal processing, if you use least square error, your time domain and your frequency domain would become the same if you draw those graphs, and it's very helpful to understand the error. All right, so let's see how we're going to minimize that E of n, that we call it in-sample error, with least squares. Okay, so you're trying to understand, you're trying to find the optimal W, which is called W star, and it's the argument minimization, so that you have to minimize that E of n, E of in-sample error of W, where our W's are in a D+1 dimensional space. So if you expand this, if you if you expand E of in, so you're gonna have y hat, y vector of y minus x w's, and we are using the least square here, and we call this f of w. All right, and I mentioned last session also some minutes ago that there are two methods in order to minimize that. The first one is the analytic solution, and the second one is the geometric one. So we're going to discuss both of them here. So now if you draw this f of w, you're going to have a shape like this, a similar shape like this, which is, this is your w, and this is your f of x, and this is your function. So we are interested in those points, such as w0, that gives you the steepest increase in the direction of the steepest increase in your graph. And another thing that I'll describe later is, so this function of this has to have a properties, we call it convex. I'll describe what the convex is. I mean, I can. So in optimizations, we call a function convex, like here, like this one. If you pick any 2 points, and you draw them together, like point A and B, that line that you draw becomes either on the function or inside a function. So this is a convex function. Whereas if you had a function like this, you would pick 2 points, A and B, and you would draw a line, and it would become outside it, like this. If you were picking these 2 points, you want to be inside. So these shapes, this is a convex shape, this is a convex shape. So you can pick 2 points, they're inside. This is the convex shape, and so on. I'll have a more formalized description of that in a couple of slides.
Just a question about x multiplied by the weight vector. I noticed in some of the formulas you use x transpose.
Yeah.
So are you just representing it as a row vector? Or sorry.
Yeah. If you expand this, it's going to be the same transpose, because we define it here. We define it here. So the x would be, so that was the transpose 1 up to n. Yeah. All right, now let's start with the first method, if you didn't write the convex property, I'll describe it in a few slides, no worries. So let's talk about the first solution, the analytical solution. So if you solve this analytic solution for the linear regression, you end up with a function that for least square, that's why we call it W of LS. So LS represents least square. And that's going to be your solution. So in statistics, this matrix has a name. So we call it pseudo-inverse. Sometimes you see without the dash in the middle, or sometimes it's two separate words. But we call this matrix X transpose multiply X. And we invert that and we multiply that to xt. We call this pseudo-inverse of matrix X. And we define it by a dagger here. So this is called dagger. Actually, this became a bloody dagger here. So yeah, X dagger is a pseudo-inverse of your matrix X. It has more or less similar properties than your invert of X, but it gives you more freedom in several situations, mostly in machine learning and linear regression. That I'll describe it here. But yeah, so now our job is to prove the final solution for our linear regression and see how did we end up with this matrix. All right, as you recall from the last session, I mentioned that when we have several number of equations, we call them n, like representing number of our data points in the raw data of our data set, and we had a number of several number of variables in a space of d plus 1. Normally, in the case of machine learning, since we had many rows and fewer columns, so it would become that our n is much bigger than d, right? So if you draw this matrix, you won't be able to have a square matrix, right? And getting an invert from a non-square matrix is not possible. So
what do you mean n is much bigger than d? D being the number of what does d represent? Sorry.
So d is a number of variables like your features.
Okay, and then n is the number of samples we have.
Yeah, like the number of rows. Yeah. So it becomes a linear equation system. All right. So one of the first things that X-dagger or pseudo-inverse helps you to accomplish is it supports non-square metrics, which is the case for most of our problems. So if you draw that, you're going to have the X as some d plus 1s and many n's, right? It's going to be a tall matrix. So just for your information, I provided some of the properties of pseudo-inverse. Just refer to your textbook, that Boyd statistics, or just Google online. You're gonna see like tons of information online. But some of the more well-known one was the first one is so your X. If you multiply your X dagger or your pseudo-inverse matrix to your matrix itself, you're going to have an identity matrix of X. And so suppose an identity of 3 would be the one that is going to have 1s here on the diagonal and then the rest of 0, right? So that's called identity. And depends on the size of the X, that would be the size of your X in both cases. So that's one of the properties of X-dagger. Also, the second property can be X-dagger exists for every matrix, which is nice for us, and also it's unique. It's not just like the real invert of matrix that you cannot have it because the matrix was not a square. In the case of pseudo-inverse, it exists for every matrix and it's unique. And another property is if your matrix X was invertible, thus you would be able to get the invert of that, like x to invert. X dagger would be the same as your x minus 1, right? In this case.
Like why?
You can have a look at the proof. But if you multiply this, you'll find out. So you multiply this to that, you'll find out. So in the case that x was a square and it had the property of being able to getting inverted, like its determinant wasn't 0 and all the other properties, you might have looked at the statistical course about that. But assume your x was invertible. If that was the case, your x dagger would be the same as that invert of the matrix. And it's good at least that we know. It represents more or less, that's why we call it pseudo-inverse. It represents similar properties with your invert, and it gives you other things as well. So another interesting property for x dagger is if you get a dagger, if you get a pseudo-inverse of your pseudo-inverse, it becomes your x as well. And the fourth one, which was the most important one that we are interested in linear regression, is it can handle non-square matrices, which is the case normally for us. Again, there are so many other properties and preconditions, but that was just a gist of those. If you wanted to have a look, you can just refer to your statistical textbook. All right. So now let's see. Everyone's done with that? There you go. So if you draw that f of x on a case that you had two w's, w1 and w0, it would become a trivial space. And so I mentioned in a previous session that you would have a shape like this, right? And so we call it in geometry paraboloid. And this is your W star that you want to reach by minimizing your function. So you might start from any of the points here. Like you might start here or here. But using the gradients, it helps you to move towards your W. Okay? If you project that into a 2D space from the top, and if you project it here, you're going to see some contours here. We call it level set. Actually, this plot is called contour plot. So each of these level sets are actually one of the points here. So like your 1, your 2, your 3. So that would be like this. If you take a look at it from the top. And each of these W's, like f of W, are the constant numbers, which you could see here. So here, here, and there. All right? So in a 2D space, your W star would become in the middle of that. So here.
Okay, I'm not following. If this is a cylinder, then
it's not a cylinder. It has this shape.
Oh, I see.
Yeah. So this one is like getting smaller, small. But if you get from the top, it becomes like this, right?
But are we limiting our scope of W0 and W1 to like just that range?
No, actually this is just for visualization purposes. You might have more W's, so you wouldn't be able to draw it, right?
No, I understand that. I'm saying like we're limiting our scope of our W0 and W1 to begin with.
Yeah. If you want to visualize it, yeah. If you want to solve it using the analytical model, you might have any number of W's, but you don't have to draw it anymore. All right, let's just wrap what let's just double stress on the thing that I mentioned about convex function. So I mentioned that a function is convex if the line segments. So we are here. If the line segment between any 2 points on a graph lies on or above the graph. So if you take a look at here, so this is also a convex function. If you pick 2 points here and you draw a line, so that line lies on or above the graph, which is cool. So that's why it has the properties that we can optimize it using the least square, or also here. Or if you pick these 2 lines, they're here, or another line here. But I mentioned if there was another type of function that you wouldn't be able to do that, it doesn't have the convex properties. So in that domain, you wouldn't be able to solve it with this method. Question?
Yeah.
Yeah.
To clarify, if it doesn't have the convex property, is that it won't work because the solution will converge on that area? Perhaps?
Yeah, you wouldn't be able to converge because at some point you might be out of the. So this is a convex property. So you might start from here, and that was your W star, right? So you go here on the next point, and then you find a gradient, and then you go down and you find here. But if it was like this, it would become non-convergent because you would become trapped in some of these solution space, and you wouldn't be able to recover to reach this point, right? Because it didn't have the convex property. Also, if you have another function like this, well, actually, yeah, this wouldn't be convex because this was outside it. It would be hard.
And then another thing is the reason why those lines that you drew, those are method of least squares, or
which lines I drew?
Like the lines across that paraboloid or whatever.
Yeah, no, I was just trying to showcase that if you pick 2 points, I just wanted to provide you visual proof that this paraboloid is a convex function, because if you pick any 2 points, the line in between lies inside or above it. That's all. But in a least square in a 3D space, you might start from here and you go either there or there or there, and think about it as a 3D space. And then the next point you're gonna go there up to the point that you hit here. You might come from from behind or there, but eventually after several iterations you might hit the W star, right?
Okay.
Yeah. And the way we pick this is another hyperparameter. In neural network, there are other optimizations like stochastic gradient descent or Adam optimizer or many other things. It just shows you how we're going to optimize it and in how many iterations. So this is like a huge problem in optimization space. Yeah, so it's pretty interesting and open as well. Open question.
Okay, sorry, one last thing. Okay, so it's great that we have this here, but like, how do we use this? Like, I just see the picture, but like, I don't know what.
Yeah, now we're going to talk about it in the next slide.
Okay.
Exactly. Okay. All right, let me just. All right. As a special case of that, using that formula, you can see that if D was 1, which was this case, you would have only W1 and W0. And that's what we discuss here. Okay, let's talk about the solution. So we are interested in minimizing f of W. Thus, we are interested in finding the derivatives for all the vectors inside that. So all of them at once, and we, and also that 0 is a vector of 0. So in statistics, this is called find the gradients of that f of W. So if you expand that, you're going to have the derivative of f by w0, derivative of f by derivative of w1, and so on and so forth, up to hit the last one, which is derivative of f divided by. So it's a gradient of f of w, and we are interested in solving that problem. All right. We define the gradient of g as g of w equal to wtv. We name it v here. So if you expand that as a linear system, it's going to be w0, v0, w1, v1 up to wvd. And if you present it in a vector notation, it's going to be v transpose w. If you take the derivative of that, so you're going to have w transpose aw, and then it becomes a plus a transpose w, and that's 2aw if in the case that a was equal to a transpose.
Sorry, why did we jump from f to g?
We define it as a gradient, so as a function gradient g.
We defined g of w to be
Because when we get the derivatives of all the elements of that fw and we equal it to 0, this notion is called gradients, so we call it g here.
Oh, so we call that we call gradient of f to be the function g. Like
Yeah.
That's the same thing.
And we're going to use this wtv later in our proof.
So where's vector v? Where does that come from? Is that the already graded? Like
Yeah, we just define it as this.
no, but so the weights are already there from the function f,
Right?
correct? And v is the what is v here? Like where does that come from before?
No, we defined v as the gradient of w equal to wt of v, right? We define it here, and we want to use it later on to prove that f of w. I'll show you the next slide. You'll understand here. So we start from here. We expand it. Y minus xw transpose. And then it becomes y transpose y minus y transpose xw minus xw transpose y. And the product of these two next, you're going to have two of these, and then you have wt, xt, xw, and finally, for your gradient f of w, you're going to have the gradient of all of them, and that's what we call it v here in the previous slide.
V is equal to x transpose times y.
Yeah. And then that was the case in our xtx, which was a was equal to at. Oh, let me just wait here so you write it.
Because there's no w in y transpose y, we can the gradient of that would be 0.
Say it again.
Because there's no w in y transpose y,
Okay.
the gradient of that would be 0, so we ignore it from our equation. Last line. I'm taking the gradient.
Here you're talking about?
The first of the three. No, last line. First unit of that equation inside the gradient.
So here?
Yeah, that would go to 0, right?
I don't. I mean, in some situations you might not have that. I'm just talking about an exceptional case that you might be able to do that, or some situation you might not.
I'm just thinking, if you take the derivative of that by the derivative of W, right? Omega, it would, for all omegas, there's no change in Y transpose Y, so would it not turn to 0?
I would say not always, but yes, sometimes it might be. Sometimes it might be. The point is, we when we take the derivative and equals them to 0, we are interested in finding the gradients, right? We're interested in finding, for your function, we are interested in finding that point that at the steepest increase or at some point decrease. So that would give us this point, right, in your graph. So I just equal them to 0. That was a vector 0. So I could have put them on the right side. So both of them are the same. All right? And through that, if you bring this side on the left-hand side, you're going to have X transpose XW. And that was, I guess, that was your T again. I'm not sure what happened here. Let me double check if this is correct. You might have skipped ahead of that. Yeah, so this one was the transpose. So yeah, you're gonna have X transpose XW equal to X transpose Y, and then finally you're gonna have your W as that pseudo inverse, and this is gonna be your least square solution. So Y hat equal to XW is your matrix X multiply XT, X, and all inverted, XT, Y. So that was the proof of the least square solution. So we would call it X dagger. Okay. All right, so that was the proof of the first solution. So we know that by the analytic solution we have the solution of linear regression as X dagger Y. So let's see if we can do that, if we can find a solution with the geometrical interpretation. So the second method. So here we have to define a function called span of X. So suppose your Y hat was equal to XW, So you could expand that to the summation of i's from 0 up to d, qi's, wi's. And we call those qi's the ith column in X, or the span of X. So we call these q's span. So these qi's could be q1, q2, up to q3, and they are a linear combination of your wi's. I'll have an example in the next slide so you can understand what a span function is. So if you were to have a look at that y hat and your true y in a geometrical format, so that your y hat in a linear square problem is the projection of your y onto a P subspace when you have this orthogonal property between the projections. So if you project that W to your subspace P, and when this is orthogonal, your y hat would be the span of y here. So we call this P space. And P would be the span of column X here. I'll have a short example, and you'll see it's pretty easy to understand. But just think about a span as a linear combination of each of your columns multiplied by your W's. And that's your zero, vector of 0.
Sorry, what's it say in the blue brackets, right? Given
Yeah, those brackets. Yeah, they're defining your Q from Q0s up to QDs. Yeah, that you're gonna use here. So and QI is the ith column in X, right? All right. So that's just, as I mentioned, is as if you project your y onto the subspace P, and this X dagger present you that. So this amount would be the projection matrix. So y hat, as I mentioned, is a projection of y onto subspace P in a geometrical interpretation. And then we can call it as a final hypothesis. So this H projects y onto the column span of X. Also, as a definition, if you want to have a definition for a span, is a set of vector spans. A set of vector spans the space if every other vector. So here, if every other vector in a space can be written a linear combination of the spanning set. I'll have a quick example in the next slide. Yeah, I'll just show you in a second. So suppose you have a matrix A here. So an A has two columns, 1, 3, 2, 5, right? You can define it. You can present it as a linear combination. So you can have alpha multiply your first column and beta multiply your second column, right? And if you solve this equation to find a linear combination of these two, and you find the alpha and beta here, right? And if you fill those two as, and you put alpha as -4 and beta as 3, so you're going to have 2, 3, right? And you can call it the span of A. I mean, actually, this is it clear now? A.
What spanning is?
Yeah. It's basically a linear combination between all your every vector of your matrix. So you want to present your matrix in a linear combination of several vectors, right? And those spans are those functions that help you do that in general. And so, sorry?
They're all orthogonal.
Yeah, they should be orthogonal like this here. And it depends on the rank of your matrix, if it's singular or non-singular. So I don't want to get into all those statistical details. But for this course, you just have to know up to this level. If you're interested in learning more, you can just have a look at other statistical textbooks. It depends on the rank of your matrix, if it's singular or non-singular, which means that if the elements of your matrix, like this, either these two columns are a linear combination of itself or not. Suppose your first column is 1, 3. If your second column were to be 2, 6, so 2, 6 is a linear combination of 1, 2, 3, right? If you multiply them by 2, you're going to have the second column. So these two columns are linearly dependent. So it's going to lower your rank of your matrix. So you would have lower number of spans as well. So there are other properties that, you know, it requires more time to elaborate. So just for now, you just know that a span of A or a span of any matrix is a linear combination of vectors that, you know, you can add with each of your columns, and they are orthogonal, right? Let me just open this again. All right, as a sort of wrap up. So for a linear regression algorithm, so we construct the matrix of input, we compute the pseudo inverse, and we return W pseudo inverse of X multiply Y, and that's going to be a solution. So that's the wrap up we normally do. I'll have like a couple of more slides if you bear with me, and then we can finish with this. Okay? So we have a variant of least square, which is called regularized least square. So it's the same least square. It was the same least square that you add another hyperparameter called lambda here, and we call it the coefficient of that. So using that, you can regularize how much you go from each direction. So it's not going to be the static on each, like each of the steps would be like this length. So with lambda, you can control if you go this or higher. So you can regularize in general your least square. So it's sort of a variant of your least square. So instead of minimizing this function, y minus xw, you add that lambda to that w, and you add it as a penalty term. How do we select that? It's through cross-validation. I'll have it, detailed definition of what a cross-validation is, but for now, just learn it as a way that when you have your training data set, you can. So this is your whole D. So you can cross-validate your lambda like by dividing this to like 30% and 70%, and you learn by this 70%, and you test that with the rest of your 30%, and you have a result, like you have a prediction, certain percentage, right? You can randomize it again, and then pick another 30% and 70%. So this is your first, and you're gonna have another 70% as your second, and this gives you another loss function, right? And you compare these two and the rest, and you pick the best one. So this is called cross-validation. You cross-validate your results between your data set, and that's how you're gonna pick a better lambda. For now, just think about it this way. And that's gonna be your final solution. So you're gonna have, equal it your gradient to 0, and then you add the lambda, and then that's gonna be your final solution. Okay? I guess I'm gonna stop here. For next session, I'll have a few slides on the nonlinear transformation, and then we're gonna start the logistic regression. If you wanted to have a look at the textbook, we are in the chapter 3. We already finished 3.1 and 3.2. So we're gonna start by 3 by 3. All right. Have a good day, guys.